Okay, we'll go ahead and get started. So what we're going to do today is we're going to complete chapter 7. And then on Wednesday, you'll have a quiz on chapter 7. And then we'll also start chapter 8. So on Wednesday, we'll have lecture on the first part of the class, starting on the chapter 8 material. And then in the second half of the class, we'll have a quiz on chapter 7. The other thing I wanted to mention and remind everyone is, so in the lab, this week is a makeup week. So if you are absent from a lab, this is your chance to work with your instructor to make up that lab. If you didn't miss any labs and you completed them all, congratulations, that's great. And it means you get a week off of lab this week. And then the following week, so next week, will be the lab final. So that'll be an in-person exam. It'll be a closed book, so no cell phone, no computer, no textbook. And I believe most of the exams will be in the computer lab where you were the last 3 weeks. Unless your instructor tells you otherwise. I know for my 2 sections, that's where we'll be because we can hold all the students at once. So come at that initial time and the final will be in there. And then that's the end of the lab. So we finished the lab a little bit early. That was intentional because we were concerned about some COVID things. So that'll wrap up the lab portion. Any questions on any of that stuff? Yes.
Will it mostly be the math equations from our labs?
So the question was, will the lab final be mostly math equations? And I would say it's a combination. Some of it's math, some of it's theory. So it'll be about the things hopefully you learned during the course of the semester in the lab. So some of the theory behind the labs in addition to some of the calculations and things like that. So it'll be kind of a combination. Any other questions? Okay, so can you see the slide over Zoom?
Yes.
Okay, I'll take that as a yes. All right, so what I'd like to do today, I'd like to go back a little bit because I forgot the homework problems last class. And so I'd like to go back and go through some of those homework problems, make sure everyone is clear on how to do those. And then we'll pick up some new material after this. So if you recall, we talked about something Z effective, the effective nuclear charge, and we said one way to calculate that is the atomic number minus something that we call the screening constant. And usually the screening constant is just the number of inner electrons. And so that's a pretty simple calculation. There is another way to do it, and I wanted to kind of go over that. So the other way to do it is using something called Slater's rules. And this is another way to calculate the effective nuclear charge because it's a different way to calculate the screening constant. And this is applicable only for elements that do not have D and F subshells. So it's kind of limited, but it is another way to do some of these calculations. And I wanted to talk about that a little bit. So when you're using Slater's rules, that screening constant S is estimated, and electrons for which the principal quantum number is larger than the value of the principal quantum number for the electron of interest, those contribute 0. So in other words, electrons that are further higher energy outside that shell, they don't have any screening constant associated with them. So that kind of makes sense. If it's a 2s electron that you're interested in calculating for, a 3s electron isn't doing any screening because it's a higher energy. Electrons with the same value of N as the electron of interest contribute 0.35. So once again, if you had, say, a 2p electron you were trying to calculate the screening constant for, the 2s electrons would have this contribution of 0.35. And then electrons with a value of N-1 contribute 0.85. So in other words, if it's one principal quantum number lower than the electron that you're interested in, it's a contribution of 0.85. And if it's smaller than N-1, it contributes 1. So if it's a true core electron, then it equals 1. So as you can see, it's similar to just looking at all the electrons and doing that simple math, but it is slightly different and gives you slightly different values. So if we take fluorine, for example, fluorine has 9 total electrons. It has 2 1s electrons, 2 2s electrons, and 5 2p electrons. If we wanted to calculate that screening constant, going back to our rules, remember these were our rules here, that N-1 is 0.85, same N value, remembering that N is that principal quantum number. If it's the same, then it's 0.35. And so what we see there is we have a total of 7 electrons in that principal quantum number 2 shell. And so remember, when we do this shielding constant, we don't count the electron that we're interested in. So instead of it being 7, it's 6 that are at that same principal quantum number 2. So 6 times 0.35. Then in this case, we have 2 electrons that are at 1s level. So that's a quantum number N-1. And so then it would be 2 times 0.85. So we do that math and we get a value of 3.8. So in this case, using the Slater rules, it would be the atomic numbers 9 minus the shielding constant 3.8 to give us 5.2. So not a huge difference in the number, but there is a slight difference because we make some adjustments to the electrons that are in that same level. In this case, N equals 2, and then the level 1 down. In this case, N equals 1. So let's take a look at a couple example problems from the homework. So the first one is 7.15 that I'd like to look at. And in this problem, they tell us that detailed calculations for the outermost electrons for sodium and potassium, you get effective nuclear charge values of 2.51 and 3.49. And so the first question is, what do you estimate that Z effective to be for the outermost electron in each of these, by assuming that core electrons contribute 1 and valence electrons contribute 0 to the screening constant? So this is that first formula that we talked about, where Z effective is just the atomic number minus the number of core electrons. So in this case, sodium is 11 is the atomic number, and the number of core electrons is 10. And remember, the core electrons is what? It is those number of electrons that fill the noble gas, closest noble gas to it. Those are the core electrons. Everything past that noble gas, those would be our valence electrons. Potassium is similar. These are both 1A elements, so they're similar. 19 is the atomic number. 18 is the number of core electrons. And so we get a value of 1. So in this case, it's telling us the shielding constant, or rather the effective nuclear charge for each of these is the same, calculating it this way. So then in part B, we wanted to do the same calculation, and we wanted to do it using Slater's rules. And so remember, down at the bottom here, we have Slater's rules where we say to calculate that shielding constant, it's 0.35 times the number of electrons that have the same principal quantum number, the same N number. And remember that principal quantum number is the number in front of each of these orbitals when we write it out. Then that's plus 0.85 times the number of electrons at the N-1 level. And then it's 1 times the number of electrons with N-2. So remember that N-2, that would put you into those core electrons, into that inner shell. So that part's kind of the same as what we did up front. This 0.35 and 0.85 factors, that's where it's a little bit different. So if we look at sodium, and we write out the electron configuration for sodium, we would have 1s2, 2s2, 2p6, and 3s1. So for one of these Slater rules type problems, that's the first thing you want to do, is you want to write out that complete electron configuration so you can see what the principal quantum numbers are for the different levels that you're having for the atom. So if we go ahead and follow our Slater's rules, we look and we see that since we don't count the electron that we're at, in this case, it would be the 3s1 electron. So we have, for that 3 quantum number, we don't have anything because we don't count the one that we're interested in. There's no other quantum number 3 electrons present other than the one we're looking at. So it'd be 0.35 times 0. We look at that N-1 level, and remember we said that's where you have 0.85 times that number of electrons. And we have 6 2p electrons, and we have 2 2s electrons. So we have a total of 8 electrons at that quantum number 2, that quantum N-1 level. So we would have 0.85 times 8. And then finally, we go to the next level, the N-2, because that takes us down to the 1s level. And we see there, we have 1, and there's for that factor, and we have 2 of those electrons. So we add all that up, and we get a total of 8.8 is our shielding constant. And then if we go back and calculate the Z effective number, it's 11 minus 8.8 equals 2.2. So what that does is it shows us that it's a slightly different value. So when we did the more simple way, we got a value of 1. Now we get a value of 2.2. So it does make a little bit of difference when we take into account some of those other levels of electrons. You get to those electrons that are more than 1 quantum number away, and it's pretty much the same as the simple way. It's that layer that is either at the same quantum number or N-1 that you see a little bit of effect. So let's do the same thing with potassium. So with potassium, once again, the first thing we would do for the Slater rules type approach, we want to write out the electron configuration. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. If we look at our Slater's rules again, we see that it's 0.35 times the number of electrons with the same N. There's only that 1 electron at the N equals 4 level, and that's the one we're calculating. So we don't count the one we're calculating, so there's no other electrons, so that would be 0. We look at the n-1 level, and that's the 3 level. And so we have 2 3s2 electrons, and we have 6 3p electrons. So we have a total of 8 electrons that are at that n-1 level. So then we have 0.85 times 8. And then finally, we want to get to the n-2 level and see how many electrons we have there. In this case, n-2 or lower, we would have 1s electrons, 2s electrons, and 2p electrons. So if we go and look, we have 2 1s electrons, we have 2 2s electrons, and 6 2p electrons. So we have a total of 10 electrons at this n-2 or more level. And so that's a case of where that 10 would be times 1. We add all that up and we get a value of 16.8. And then we would go and take 19 minus 16.8 and we get a value of 2.2. So the next part is which gives a more accurate value, the simple approach of the Slater's view. So for each of these elements, Slater's rule told us we got a value of 2.2. If we think back to what I said in the beginning, the calculated values were 2.51 and 3.49. So those 2.2 values are closer to that 2.51 and 3.49 up at the top than 1 is. So the Slater rule does give you a little bit better data than the simpler. Then D asked, does either method of approximation account for the gradual increase in effective nuclear charge when you move down a group? And the answer to that is no, because we got the same answer for each of those. So if we just went by our Slater's rules-based calculation, we would think they were the same, but a little more sophisticated calculation would show that they're not. So these simple ways to do the calculation are useful, but they're not perfect. And then finally, predict the Z effective value for the outermost electrons in rubidium based on the sodium and potassium calculations. So the sodium calculation that we were given was 2.51, potassium was 3.49. Rubidium, which as we go down the table, what would be a good guess on that? And a good guess is if we look when we went from sodium to potassium, there was a change of about 1. And so then from potassium to rubidium, you could make a case that the change would be about 1. This goes back to that whole periodic trend type thinking. And so then a good estimate would be 3.5 plus 1 would be 4.5. So what I would hope you would get from this homework problem is understanding that you can calculate Z effective, at least for this class, 2 different ways. One is the simple Z minus S, where S is that shielding constant. And in that case, it's just the number of core electrons. Okay, so it's atomic number, which is Z, minus the number of core electrons. And the core electrons are the number of electrons that make up that noble gas portion. The other way is to use Slater's rules, which is down at the bottom of the page there, and it has some factors depending upon the quantum number that the various electrons are at. So maybe it's a 0.35 value, maybe it's 0.85, maybe it's 1. Bases on this number, whichever one of these you use, is based on the principal quantum numbers. And just to remind you again, the principal quantum number is that number in front of the letter. So 1s or 2s or 2p. That number in front of the letter is the quantum number in. And so that based on what that quantum number is for those electrons, that tells you which of these factors you should be using to calculate that shielding constant. And so then once you go through that calculation, using that information about the quantum numbers, principal quantum numbers, then you can go ahead and subtract that value from the atomic number to get the Z effective value. So remember, if you're doing a Slater's rules type calculation, first thing you want to do, write out that electron configuration. That allows you to know what principal quantum number is associated with the various electrons. After you know that, then you can apply those factors that are Slater's rules, and then you can calculate that shielding constant. And then from there, you can get the Z effective value. Okay. So just to remind everyone that last time we did talk a little bit about ionization energy, and that's the minimum amount of energy required to remove an electron from the ground state. So ionization energy is one that we talked about, where you're removing electrons. The other thing we talked about was electron affinity. So electron affinity is the energy change accompanying the addition of electron. And so one, you're removing an electron. The other, you're picking up an electron. Electron affinity, you're picking up an electron. The key thing about each of these is that you're forming an ion. And this is that gas phase chemistry that we talked about a little bit, that leads to mass spectrometry and some stuff like that. But in one process, you're giving up an electron. The other process, you're picking up an electron. And so electron affinity, you're forming anions. Ionization energy, that's forming cations. So that's important that you remember that distinction. I think the homework for that part was pretty much self-explanatory if you worked through it and saw the answer, so I'm not going to go over that. But I am going to start and go over the last portion of this chapter, and that's where we talk about metals, nonmetals, and metalloids. And so early on, we talked about, when we first started looking at the periodic table, we talked about how things in the upper right-hand corner are the nonmetals. Things in the left-hand side of the periodic table are the metals. And then there was that kind of stair-step dark line that starts between boron and aluminum and kind of goes down. And that the elements along that are the metalloids. And the metalloids are simply ones that have some properties that are metallic-like and some properties that are non-metallic-like. And you see a couple things on here is that we see an arrow at the top of this table telling us that as we go from right to left on the periodic table, we increase in metallic character. And the only disclaimer I'll say is hydrogen is an exception, and we'll talk about that a little bit later. But let's not focus on hydrogen right now in terms when we're talking about metals and nonmetals. But for the rest of the elements, as you go from right to left, you increase metallic character. And when you go from top to bottom in one of the columns, so in other words, 1A, 2A, things like that, you increase the metallic character as well. One of the big things about metals is that they tend to form cations. So if something forms a cation, does that mean it's gaining or losing an electron?
Losing.
Losing, right. Because now if you have less negative charge, then it becomes positively charged. So metals like to give up electrons. Nonmetals, which we said were on the right-hand side of the periodic table, they like to form anions. So that conversely means they like to pick up electrons. So metals, nonmetals kind of really match up well, is that the metals like to give up an electron, the nonmetals like to receive electrons. And so what you'll see is from a charge balance perspective, you'll see all of these, they have some highlighted metals here, more common ones. And we see what those have in common is they're all positively charged. In the right-hand side, which is our non-metals, we see those are all typically negatively charged. Hydrogen's the funny one because you see over on the left, it's listed as H+, and over on the right, it's listed as H-. The vast majority of the time, hydrogen is H+. Okay, so that's what we're going to focus on. There are examples of H-, but we're not going to be too concerned about that because for most of the time, it's H+. So when we think of metals, and we think of nature, most elements in nature are metals. And that makes sense. You know, we go back to the periodic table here, and we see there's a heck of a lot more things on the left-hand side than the right-hand side. The only disclaimer I would kind of make on that is we look over the nonmetals, and we have carbon, nitrogen, oxygen. Those are pretty common elements. And so there's a lot of stuff that makes up that. So if you went on the amount of stuff, you'd have a lot of those. But in terms of sheer numbers of elements, there's a lot more metals than nonmetals. So metals in general tend to be kind of shiny. One big property that they have is they're able to conduct heat and electricity. They're malleable. That means you can kind of bend them around. You can shape them when they don't break. They're ductile or pliable. And so the one I always think of when I think of that, the shaping and the pliability in that is I always think of wires, electrical wires, where you think of electrical wires, you could bend them and twist them and turn them and all that, and nothing happens to them typically. And yet they still are able to conduct electricity. Solids are usually, metals are usually solids at room temperature. If you've ever seen mercury, that's an exception. Mercury is a really dense liquid at room temperature. And finally, they have a low ionization energy. And we know that means that they form cations easily. And that's what we talked about just a few minutes ago, is metals almost always form cations. When we think of metal chemistry, and we'll have some example reactions here at the end of the chapter, but when we talk about metal chemistry, when we form compounds that arise from the reaction of metals and nonmetals, they tend to be ionic. And that makes sense. We said metals like to be positively charged. They like to be cations. Nonmetals like to be negatively charged, anions. Metal oxides tend to be basic and they react with acids. If we talk about the nonmetals a little bit, as we've said, those are on the right-hand side of the periodic table. They can be solids, liquids, or gases, depends on the element. They're not shiny like the metals, and they're poor conductors of electricity. It's hard to work with them without breaking, things like that. And they have a negative electron affinity, so they like electrons. And so that means they form anions readily. And it means they're reactive too, typically. So if you have substances that contain only nonmetals, we call those molecular compounds. And so we've talked a little bit about organic chemistry and organic compounds. All of those are compounds that are made up of nonmetals. And so most living things and stuff like that are carbon-based, and those would be molecular compounds. Non-metal oxides tend to be acidic. And so if we just kind of look at the properties between metals and nonmetals again, we see metals tend to be shiny, they have some color sometimes, a lot of them are silver. The nonmetals don't really have much luster to them. So in other words, if you're walking along and you saw a nonmetal on the ground, you probably wouldn't pick it up, whereas the metal, it would catch your eye. The metal solids are easier to work with, so they don't break, you can bend them, you can extrude them, things like that. The solids for the nonmetals are usually brittle. Metals are good conductors of heat electricity, nonmetals just the opposite. Metal oxides are ionic solids that are basic. The nonmetal ones form acidic solutions. And the metals in aqueous solution tend to be cations, as we said, because they like to donate electrons, and then the nonmetals tend to be anions, or something called an oxyanion in aqueous solutions. The metalloids have, as we said before, have some properties of metals and some properties of non-metals, so they're kind of in between. And a lot of the metalloids you can find in computer chips. So when we talk about group trends, and remember, group is a column, okay? When we say a group of something, we're talking about a column on the periodic table. And so those columns tend to have similar properties, and sometimes you see a bit of a trend within the group. And the groups, just to remind you again, 1A are the alkali metals, 2A are the alkaline earth metals. So that's the two way over on the left-hand side, okay, on the periodic table. That's those first two columns on the periodic table are the 1A and 2A groups. We go over to the right-hand side, and those last three columns, those are group 6A, which is the oxygen group. 7A are the halogens, so that's chlorine, fluorine, things like that, and 8A are the noble gases. So we'll talk about these a little bit, and we'll talk a little bit also a little more about why hydrogen is considered a non-metal. Even though in the periodic table, it's usually listed over in that 1A group with the metals. So the alkali metals, once again, that's that 1A group. If you ever see any of that metal, it's really soft. And it's usually not found in its elemental form. If you ever do see elemental of these, it tends to be kind of a grayish looking thing. And as you can see in that picture, it's kind of interesting. I don't know what that is. It could be potassium or sodium, I don't know. But you can literally cut it with like a butter knife. You can cut the metal with a butter knife. It's that soft. They tend to have low densities and melting points, and they have low ionization energies. And so what that tells us is it's pretty easy to knock off that lone s electron. So the thing that all these have in common is their valence electron is just one electron in an S shell. So whether it's 2s, 3s, 4s, 5s, 6s, whatever, there's just one. And so that's pretty easy to knock that electron off. You knock that electron off, then you have a cation. You see some trending here in melting point. You see the melting point going down as you go down the column. You see the density going up as you go down the column. And you see the atomic radius getting bigger as you go down the column. And so you think about it, that atomic radius is going to get bigger because you're adding shells, right? You're going from 2s to 3 to 4 to 5 to 6, so you're getting bigger. And then finally, ionization energy going down as we go down it. So it's telling us as we go down, it's easier to ionize those elements. So this is the kind of trending stuff that you would want to be familiar with. These alkali metals, whether it be lithium, sodium, potassium, are kind of infamous for how exothermic they are. So if you take a little bit of this, one of these metals and cut it, and like I said, it's pretty soft, so you can cut it with a butter knife, essentially. You cut it and you toss it in water, it's a pretty violent reaction. And so even small amounts are really kind of shocking how much it is. These pictures don't really do it justice, I can tell you that. So let's talk a little bit about alkali metal chemistry. So depending upon which element you're talking about, you get a little bit different way it reacts with oxygen. So lithium, for instance, if you react it with oxygen, you form lithium oxide, Li2O. If you react sodium with oxygen, then you would form sodium peroxide. So a little bit different. And then potassium, rubidium, cesium, those form something called a superoxide. Superoxide is an O2 with a minus ion. So it's kind of an odd thing. But these superoxides, these three elements, when they react with oxygen, can form a superoxide. And the M in this case just means any one of those metals. So instead of writing them all out, it's just shorthand for that. So in each case, you have one of these elements reacting with oxygen, and yet you form a different thing. The lithium, a simple oxide, sodium, a peroxide, and then these other three form a superoxide. So you do have some differences in the chemistry there, even though it is the same group. Another interesting thing about alkali metals is you can often figure out which metal it is by burning it in a flame and seeing what color the flame is. And what happens is when you put the metal in the flame, that has enough energy to excite it to a higher energy level. And then when it comes back down to that ground state energy level, it emits at a particular wavelength, and that wavelength would then be the color that you would see. And so you see lithium, sodium, and potassium, you kind of see the different colors there, where lithium is a reddish, sodium is a yellowish, potassium is more of a purplish, bluish color. And so that's that electronic transition that we talked about. Remember before we talked about quanta of energy and things like that. This is one way of doing this. This used to be a really, really popular Gen Chem experiment where you get an unknown and you'd have to put it into the flame and see the color and figure out which one it was. I think it's not done as much anymore for probably people don't like having all those flames around anymore. But that used to be a real common Gen Chem experiment. So let's talk a little bit about the alkaline earth metals. So the alkali metals, remember, were that first column, group 1A. Alkaline earth is the second column over. And so that's the 2A group. And what we see there, when we look at these, we see at their electron configuration, what they all have in common is they have that noble gas core, whichever one that might be for that particular element. And then we have two s electrons. So whether it's the 2s level, 3s, 4s, 5s, 6s, that part varies. So that principal quantum number varies. So the energy level varies. But what's in common is we just have an S level that's full. Similar to the others, we see a little bit of trending going on. We see density increasing as we go down. We see melting point pretty much decreasing as we go down. We see magnesium's a bit of an outlier there. We see the atomic radius getting bigger as we go down. That makes sense because we're going from principal quantum number of 2 all the way to 6 as we get to those bigger elements. And we see the ionization energy goes down as you go down the level. So it's a little bit easier to ionize barium than say beryllium, for instance. And once again, that makes sense because those outer shell electrons aren't going to be as tightly bound because they're further away from the protons in the nucleus. The other thing I want to point out is that these, when they form ions, like to lose both of those valence electrons. And so these beryllium, magnesium, calcium, these elements like to be a +2 charge. The 1As like to be +1, the 2As like to be +2. And if you don't want to remember the thing about the electron configuration, just remember column 1 +1, column 2 +2. So the reactivity is a little odd for alkaline earths. It tends to increase as you go down the group. So for instance, you see beryllium doesn't react with water, magnesium reacts only with steam, but the other ones react readily with water. So it's a little bit different as you go down the column. Let's go over to the other side and look at group 6A. So group 6A is kind of interesting because it has metals, metalloids, non-metals in it. So it's kind of a mixture there. The 1 and 2A, those are all metals. 6A is when we kind of start hitting that stair step, that metalloid stair step. So we get a combination of them. So, and we also see here that we have some different types of electron configurations. Now we're getting into, so like selenium, tellurium, polonium. Well, selenium and tellurium we see have d electrons, so that starts getting introduced into it. Polonium actually has d and f electrons. So it's similar in that we have outer shell with s electrons and p electrons. So we see in each case we have 2 s electrons and 4 p electrons for each of these. But those inner shell electrons, there's some other stuff going on there with d electrons and also d and f electrons. So that makes it a little bit different. And that's one reason why as we go down the column, they're not all metals or non-metals or whatever. It's kind of a mixture. So oxygen, sulfur, selenium, those are non-metals. Tellurium is considered a metalloid. And then polonium, which is radioactive, that's a metal. Oxygen typically has a -2 charge, but then you see, on the other hand, polonium, because it's a metal, has a positive charge. So we don't have that nice little 1A is everything +1, 2A is everything +2. 6A is a little bit more of a mixed bag of things. We also see, we do see that the ionization energy kind of decreases as we go down. And one interesting thing about oxygen is that it can exist in 2 elemental forms. So oxygen gas O2, that's the stuff we're breathing and things like that. But the other one we hear a lot about, especially when we talk about environmental things, is we hear about ozone. So ozone is O3. And ozone is one of the typical ways that oxygen can exist. We go over to the 7A group. And the nice thing about getting over to 7A is now we're back to where everything there is a nonmetal. And so the halogens, which is the group 7A, so that's fluorine, chlorine, bromine, iodine, things like that. That likes to pick up one electron. So halogens are usually a -1 charge, so it picks up one electron. Any thoughts on why it likes to pick up one electron? If we look at its electron configuration, we see they all have 2s electrons and 5p electrons. So irregardless of the level, there's 2s electrons and 5p electrons at that largest principal quantum number. And if you think about the p shell, a full p shell would be 6 electrons, right? So it's really a nice fit to get to that, everything filled up by picking up one electron. You pick up that one electron, and then you're back to that noble gas configuration, which is a real stable configuration. So because of this high electron affinity, they're usually anions, and they'll react with metals to form metal halides. So remember, the metals are typically positively charged. These halogens like to have a negative charge, so that's kind of like a match made in heaven, and so they like to react together, and that's that metal halide reaction that's mentioned at the bottom. And then finally, noble gases. So noble gases at one time were called inert gases. And that's because they don't really react much. They really have a stable electron configuration. And so they tend to not readily react. You can get them to react, but you got to put a lot of energy in. And you see those, if you look over on the far right-hand side of the table, and you look at those energy values there for ionization, you see some pretty big numbers. You see 2,300, the lowest one is 1,000. Kilojoules per mole, and just by contrast there, so those are pretty good numbers there too, but these are even more difficult to ionize. We see that atomic radius really goes up as you go down the column, and we see the density really has a big change. You look at helium at 0.18 and then radon at 9.73. So real increase in density as you go from helium to radon. So the interesting thing about the noble gases is I think we're all familiar with helium. You know, you think of going to the kids' parties and you blow up the balloons and it floats away. Maybe you suck some helium in and makes your voice sound funny, that kind of stuff. The last one, radon, that's where if you've ever bought a house or your family's bought a house, a lot of times you get radon testing. This is what they're talking about here. Neon, that's the gas that's in the cool lights that people make. And so the argon, krypton, and xenon, those are more chemistry applications. But the other three, you know, are things you hear about pretty often just in normal non-chemistry world stuff. So they have large ionization energies, and like I said, it really does take a lot of energy to get things ionized. There's a branch of chemistry called atomic spectroscopy, and argon is used a fair amount in that. So you can ionize that, but it really takes a lot of energy to do that. So let's talk about hydrogen a little bit. With hydrogen, it has a 1s1 electron configuration. And so that is similar to that 1A, those alkali metals. The reality is, though, that it really isn't a metal. And so even though we think of acidic compounds like HCl as having H+, it's really more of a covalent bond in reality. You can, when reacting with metals, form hydride ions, H- form, so that does exist. But like I said before, usually when we think of hydrogen, we think of it as a +1. So that's why it's over there on the left-hand side, even though it's not considered a metal. Let's take a look at a couple of homework problems here. These are some of the example reactions, and the expectation is if you were given some of this information, you'd be able to figure out what the reaction is. So let's look at 7.65. Let's see here. So in 7.65, they ask for write the balanced equation for these following reactions. So the first one is barium oxide plus water. So barium oxide would be BaO. So in other words, the oxygen has a -2 charge, barium +2 to make that neutral molecule. And then react that with water, you get barium hydroxide. So what your takeaway on this is that this is a reaction of a metal oxide. So barium oxide, that's a metal oxide. And then you put that in water, what happens? Well, what happens is you form a metal hydroxide. So we talked earlier about some of these classes or types of reactions. This would be a metal oxide plus water reaction to give you a metal hydroxide. So we need to understand that's what barium oxide does when placed in water. And then we would want to make sure everything was balanced. In this case, it all balanced. There were no coefficients that were needed, so that part didn't have to be changed once we wrote it out. The next one, iron 2 oxide. So in other words, another metal oxide plus perchloric acid. So perchloric acid, obviously, is an acid, but we need to think back from a few chapters ago to remember what the molecular formula for perchloric acid is. This is one of those group of acids, those CLO type acids that we talked about and had like several of them. So iron 2 oxide, FeO, plus the perchloric acid. And in this case, we would know that the iron forms with the chlorate to give us FeClO4, but in order to balance things out, we'd have to have 2 ClO4 there. So that's why there's the 2 after the parentheses. Because remember, we were told it was iron 2, so the charge on iron is +2. ClO4 has a -1 charge. So we need 2 of those. And so we form that salt, that iron salt, and then plus water. To get things to balance, we have to go back and see that we have, for instance, 2 chlorines on the right-hand side. So we have to put a 2 in front of the perchloric acid molecule to get that to balance. So on this one, we had a couple of things that we were doing. We needed to remember if we have a metal oxide plus an acid, that we form the salt, the metal salt plus water. Then we needed to remember the charges on the different anions and cations, and then go back and then balance things out so that we had a balanced chemical equation that resulted in putting a coefficient of 2 in front of the perchloric acid. Excuse me. You needed to remember the structure for iron 2 oxide. You needed to remember the structure for perchloric acid. So once again, there's a bunch of stuff you need to remember here. You need to remember how the reaction goes. You need to remember what those chemical formulas are for those, in this case, iron oxide and perchloric acid. And then you needed to have everything balanced. The third one, sulfur trioxide plus water. So sulfur is a non-metal. So the first two are metal oxides. In this case, it's a non-metal oxide plus water, and that forms an acid. So in this case, it forms sulfuric acid. So we go and we do that exchange to form the sulfuric acid. And we go back and make sure everything's balanced. It is the way written, so we didn't have to add any coefficients to it. But the things we needed to remember were non-metal oxide plus water gives us an acid. We needed to remember what sulfur trioxide, what its molecular formula was. And we needed to remember the molecular formula of sulfuric acid, which is that H2SO4 on the right-hand side. So once again, on these types of questions, you need to think about what class of compounds we're reacting. And then based on that, what is the likely product? The first one, a metal hydroxide, the second one, a salt, the third one, an acid. And so the other thing you needed to remember was just what are the molecular formulas for each of these compounds. And then finally piecing it together to have the reaction equation, and then making sure that it's balanced. Let's do the next one, D, carbon dioxide plus NaOH, sodium hydroxide. And so carbon dioxide is CO2, sodium hydroxide is NaOH. So once again, we have a non-metal oxide. So we look at CO2, we got oxygen, we've got carbon, the carbon's a non-metal. So it's a non-metal oxide. In this case, it's plus a base. So sodium hydroxide, because it's got that OH there, that tells us it's a base. So if we have a non-metal oxide plus a base, we form a salt and we form water. So in this case, the salt is sodium carbonate. And so we would have to remember a few things here. One is we have to remember what the molecular formula was for the carbon dioxide and the sodium hydroxide. So the CO2 and the NaOH. We need to remember the charges on things. So sodium is +1 because that's that 1A group. Hydroxide is an anion, that's typically -1. And carbonate is typically is -2, so that's why we know we need 2 sodiums with that. And then we are able to piece together our reaction of CO2 plus 2 NaOH plus Na2CO3 plus water. We have to put the 2 in front of the sodium hydroxide to balance out the sodiums on each side. And then if we go ahead and check, then everything else balances out as well. So 4 different types of reactions we looked at here. We looked at a metal oxide plus water in the first to form a metal hydroxide. We looked at a metal oxide plus an acid to form salt plus water in the second one. In the third reaction, we looked at a non-metal oxide plus water to form an acid. And then finally, we did a non-metal oxide plus a base to form the salt and water. So what I would suggest, take a look at these. I think there's some other similar problems in the homework. Get comfortable with identifying what type of reaction it is. and then thinking about how you would piece that information together to write out the full reaction of what would take place. Okay, let's look at 6.9. So in 6.9, once again, it's asking to write a balanced equation for the reaction. And the first one is potassium metal and chlorine gas. So once again, you would see the potassium reacting with the chlorine to give you potassium chloride, KCl. And then it would be a matter of balancing things out. So potassium plus chlorine, we know that potassium wants to be +1, that's that 1A group. We know chlorine is one of those halogens, the 7A group, and we said that always likes to be -1. So we would have 1 potassium goes with 1 chlorine because the charge is balanced. After we did that, we'd go back and see that, well, we had 2 chlorines on the left-hand side of the reaction and the reactant side, so we're not balanced. So if we go and put a 2 in front of the potassium chloride on the right-hand side, our chlorine's now balanced, but we've got 2 potassiums. We only had 1 on the reactant side, on the left side. So we'd have to go back and put a 2 in front of that potassium. So by adding those coefficients in front of the potassium on the left-hand side and the KCl on the right-hand side, now we can go back and add things up and see we have 2 potassiums on each side and 2 chlorines on each side. So that balances. So the next one, strontium oxide, is added to water. So we have to think back, well, what's our charge of strontium? That's a +2, oxygen's -2, so SRO plus the water. And then we would form strontium hydroxide. So it'd be SR, which was +2, and OH, that hydroxide ion is -1. So we need 2 of those hydroxide ions. And in this case, just by doing that, everything balanced. So we don't have to do anything further to that. We don't have to add coefficients or anything. The next one, C, lithium metal and oxygen gas. So this was one of our examples that we talked about a little bit before. Lithium reacts with oxygen to form lithium oxide. Lithium, we know because it's in that first column, likes to be +1. Oxygen likes to be -2 for an oxide. And so we would need 2 lithiums to balance the charge of the oxygen. We see here, though, that we're going to have to play around with the coefficients a little bit because we have 2 oxygens on the left-hand side, reactant side, and in the product, we just have 1 oxygen. So we need to balance that out by putting a 2 in front of that oxygen. Well, that gives us 4 lithiums now. 2 times 2 is 4. So we had to go back and add a 4 in front of the lithium on the left-hand side to get the reaction to balance. And then finally, D, we're adding sulfur and sodium together. So in this case, we know sulfur is usually -2. Sodium is +1. So our product will be 2 sodium, 1 sulfur. We have to go back and balance things because now we have 2 sodiums on the right-hand side. We put a 2 in front of the sodium on the reactant side, the left-hand side. Then we have the sodium's balanced, the sulfurs are okay, and we have our balanced reaction. Okay, let's look at 771. So in 771, we talked about how alkali metals react with hydrogen to form hydrides and react with halogens to form halides. So they want us to write a balanced equation for the reaction of fluorine with calcium and the reaction of hydrogen with calcium. And then they ask, what's the oxidation number and electron configuration of calcium in each product? So at the top, there's our reaction for calcium plus fluorine. So calcium's typically +2 because it's in that 2A column, and fluorine is typically -1 in that 7A column. And so calcium plus 2 fluorines. So CaF2. We do calcium with hydrogen. It's kind of the same, similar thinking. This is one of those instances where hydrogen is -1, even though usually it's +1. And we get that calcium H2. So in each reaction, the calcium oxidation state changes from 0 to +2. So how do we know that? Well, the calcium in each case has a little S in parentheses behind it. So when you see that little S there, that means it's a solid, but it also means its oxidation state is 0. So that's whether it's calcium or something else. So we know that that is 0. When we go over to the product side, we see now calcium is with the fluorine or with the hydrogen. And let's just focus on the fluorine one first. We know that the oxidation state of fluorine is usually -1. So that's a pretty safe assumption. So if that's -1 and we're balancing this out in charge-wise, then that means there's 2 -1s for a total of -2. That tells us the calcium had to be +2 to balance it out on that CaF2 molecule. So that's how we know that the oxidation state changed from 0 to +2. So in other words, if it went from 0 to +2, it lost 2 electrons, right? And that makes sense too, because we said before that that's what metals like to do. They like to lose electrons. And calcium in particular likes to lose 2 electrons because of where it's at on the periodic table. So in each case, calcium is oxidized, and the F and the H are both reduced. We say they're reduced because they picked up electrons. So if that calcium, remember we talked about redox reactions, if something's reduced, something else has got to be oxidized and vice versa. So if calcium's giving up 2 electrons, something else had to pick up 2 electrons. And in these cases, it's fluorine and hydrogen. So that's kind of the logic on this problem is what you would want to do is you want to look at those oxidation states. And this is something we did, I don't know, chapter or 2 ago, I forget now. And that's where we kind of use that oxidation state of balancing out the charge in the molecule to see how things are changing. We needed to remember that the solids, in this case, the calcium, because it's a solid, it has an oxidation state of 0. When it goes and then forms a compound, then we can use what we know about just where calcium is in the periodic table. We know that that's one of those 2A elements. Those 2A elements, they're metals, so we know they like to be positively charged. Since they're metals, we also know they like to donate electrons. So that +2 is a pretty good guess. It kind of matches with the fluorine, which likes to pick up an electron. And by having 2 of those, we balance the charge for that molecule. So that's the kind of thought process you would want to use on this type of problem is using that information that we've been talking about that we get from the periodic table to have a clue about what oxidation states things might want to go to. Do they want to give up electrons? Do they want to accept electrons? Things like that. Okay, so those are a few of the homework problems. I would suggest taking a look at some more of those and get comfortable with this reaction type thing. There's a fair amount there that you just have to memorize. And that's it for today, unless anyone has any questions. I just want to remind everyone again that we have the quiz on Wednesday on this chapter, chapter 7. So we'll start on Wednesday, the first portion of the class. We'll start on chapter 8. Then the second portion will be the quiz on chapter 7. The homework, this and the rest of the homework is posted. If you want to look it up and try some of the other problems, I would suggest that you do. And then that'll be it for today.